Welcome, everyone. So it's really a great pleasure to have Benedikt Bunz with us here today. Benedikt is a final year PhD student at Stanford, where he's supervised by Dan Bonnet. And he works primarily on applied cryptography, but also on distributed systems and game theory, with a strong focus on problems emerging in the blockchain space. And his research has already had great impact on both practice and theory, as he will explain. And in particular, he's going to tell us how his work has been addressing a number of drawbacks in existing blockchains, and also how it contributes overall to the development of a science behind this sort of blossoming space of blockchains. And so without any further ado, we'll leave the virtual stage to Benedikt.
Thank you very much for the kind introduction, Stefano. So today I'll tell you about improving the privacy, scalability, and ecological impact of blockchains. Blockchains have received a tremendous amount of hype and speculation. But if we look beyond all of the noise, there's some real transformational utility of blockchains that is building. For example, blockchains are being used to avoid currency controls by oppressive governments, and even traditional currencies like the dollar and the euro, and getting transferred using blockchains as so-called stablecoins. In 2021, stablecoin transfers exceeded $5 trillion. I work on the science of blockchain, which is the research field that is emerging around this technology. And it's a particularly exciting field because it is so multidisciplinary and combines so many different areas. So you have areas from computer science like cryptography, which is used to authenticate transactions and provide privacy for them. But you also have game theory, which deals with how to incentivize users such that they act honestly. But interestingly, there's also all of the areas outside of computer science that deal with blockchains. So for example, law and policy might be concerned with how to regulate blockchains or how assets on a blockchain correspond to real world assets. My work is on the computer science side. I'm an applied cryptographer, but my work also touches some distributed systems and game theory. But of course, it is influenced by factors on the right here from the non-computer science side. And also this space is an amazing space to be able to collaborate with many different peoples from all of these areas. So what are decentralized blockchains? Well, a decentralized blockchain is first and foremost a public shared ledger. So a ledger that everybody has access to, can read from and write to. And this public ledger gives the system a high level of transparency. So everybody can check that everything that's going on is valid. Additionally, this ledger is not controlled by a single party, a single centralized party, but instead it is controlled through a distributed consensus, which decentralizes the control of it. And overall, the value proposition of these blockchains is to enable networks with strong networks effect, but without requiring a central monopolized coordinator. So are blockchains the end-all be-all, the solution to all of our problems? Well, unfortunately, if we look at blockchains today, the reality seems to be that they still have very significant problems. So for example, if we look at the transfer fees of blockchains, they can be in the tens or even hundreds of dollars for blockchains like Bitcoin and Ethereum. Additionally, these systems have very bad privacy because everything is publicly available. It can be that you can see the sender and the receiver and the amount that is being transferred on the blockchain, which is obviously bad for privacy. And additionally, especially for Bitcoin, this all comes at an incredibly high cost because the Bitcoin's energy usage and electricity usage is on the level of nation states, so something like Egypt or Sweden. And this is incredibly wasteful and seemingly completely unacceptable in the time of climate change and ecological crisis. My work is on solving these problems. So I build systems and tools and primitives that address these problems head on. I work on something on zero knowledge proofs, which enable better privacy for these blockchain transactions. I work on tools surrounding verifiable computing, which allows you to outsource the processing of transactions to an untrusted party. And finally, I've invented and defined and designed so-called verifiable delay functions, which are a key tool for building green and fast consensus systems. This all has been joint work with 20 collaborators from 15 different institutions. My work has also had significant practical impact. So for example, Bulletproofs, which I'll talk about today, is deployed in many different systems. So for example, Monero, the largest private currency, the largest private blockchain, or for, also Signal's mobile coin. And verifiable functions of VDFs power multiple non-wasteful green, so-called green blockchains, such as Chia or Filecoin, and are also going to be a key tool for the upcoming upgrade of Ethereum to an ecologically friendly consensus system. So where do all of these problems on blockchains come from? Well, I would argue that there's a common problem here, which is the data that gets put on the blockchain. And in particular, in a blockchain, you have different transaction blocks that combine a set of transactions, but they have to get seen and verified by every single party in the system. So for example, all these users, usually called miners or validators, have to verify all of the transactions for everybody in the system. So why is this problematic? Well, this can be problematic for privacy, because if all of the transaction details are public, well, then it's easy for everybody to infer private information or information about the transaction. It can also be bad for scalability and high fees, because if I need to broadcast all of these transactions, all of these information, then this can easily lead to congestion, which then in turn drives up the fees. And finally, this can be incredibly wasteful, in particular if the so-called proof of work algorithm is used in order to elect the leaders for this consensus system. I'll talk about this a little bit more later, but this is the wasteful part of blockchains like Bitcoin. Fortunately, though, there is a common paradigm that allows us to address these challenges. And this is the so-called proof paradigm. So we are often faced with a similar situation in these blockchain systems, where I have one user that creates some data, for example, a transaction, and this data may be particularly large or revealing and may reveal some private information. And then usually this data gets broadcasted to all of the users in the system, which then have to process it in some way. So they have to, for example, verify the transaction. The proof paradigm tries to improve on this by putting a layer on top of this. So instead of broadcasting the data directly, we first pass it through some magical proof protocol. We'll see some examples of these proof protocols later. And the proof protocol outputs a certificate. And the certificate says that the data is valid and has the right properties. We can then, and while the data itself may be particularly large and revealing, we can design certificates that are incredibly small and private. We then forward the data to a so-called verify protocol that is run by all of the users in the system, and they simply check, the verify protocol simply checks the certificate and can ensure that the data has the right properties. So the core idea of the proof paradigm is to use proofs and certificates to outsource computation, but not give up on security, because these certificates, they certify the correctness of the system. So what are a few examples of these proof paradigms? Well, one of them are these zero knowledge proofs, which allow you to show that something is true without revealing why it's true. So they enable you to not leak data. The certificate wouldn't leak any data. And this can be very helpful for privacy. Additionally, there's something called verifiable computing, also closely related to zero knowledge proofs, which allows you to outsource the processing of transaction to one party, which can allow you to process much more transactions in parallel without, again, having to give up on security. And thirdly, there are verifiable delay functions, which I'll talk about today, which is a proof-based leader election and consensus protocol. And this is an ecological alternative to the wasteful proof of work algorithm. So in the first part of the talk, I'll tell you about how we can achieve privacy using zero knowledge. And in particular, I'll focus on a work called Bulletproofs. So in order to understand how Bulletproofs works, we first have to understand how transactions today look like. So this is a simple Ethereum transfer of value. And it turns out that we can actually infer a lot of information. So this is a screenshot that I took of a so-called public block explorer, where you can see all of the transaction details. And in particular, you can infer who the sender and the receiver are and how much money is being transferred. So there's 500 milli-ETH that is transferred from one user to another. If you're wondering why there's 500 milli-ETH that go in and 501 milli-ETH that go out, well, the difference is the transaction fees that get paid to the miners or validators who process the transaction. So all of this being public has a lot of implications. And in particular, if we focus on the transaction amounts being public, this has a lot of implications both to individual users who want to use the system, but also to businesses who might want to use them. So say I'm a company and I want to pay my employees on Ethereum, maybe using one of these digital versions of traditional currencies. Well, then this would imply that all of my salaries are completely public on the blockchain, and it would be easy for others to infer exactly what the salaries are. Additionally, if I run, for example, my supply chain on the blockchain, so say I'm a car manufacturer, I buy some tires, then a competitor would be able to infer what the prices for these goods are that I'm buying, something, again, important business secrets that I might want to keep private. And another example that sort of a real world example where privacy was important in a surprising way was the so-called Constitution DAO. So this was a fundraising effort that happened on the blockchain where some users got together and wanted to fundraise money in order to buy the physical copy of the US Constitution. So this was auctioned by, I think, Sotheby's, and people did a smart contract, and within, I think, a week or two, they raised $40 million in order to buy this US Constitution. However, because the smart contract is public and all the data associated with the smart contract is public, everybody could see the precise bid amount that they were going to bid. And then it turns out that they were actually, so everybody could exactly know that they were going to bid $40 million. And then they were actually outbid by a billionaire, Ken Griffin, who I think outbid them by a marginal amount and ended up winning the auction. So that was kind of a funny example of where privacy is important in applications. So a natural goal is to make these transactions private. And one level of privacy that we might want to achieve is that only the sender and receiver should be able to see the details of the transaction. So how do we do that? Well, as a cryptographer, the first thing that comes to mind is we simply encrypt the transaction. So we use some encryption scheme, encrypt the transaction, and then everything is going to be private. But the problem with it is that in these blockchain systems, miners need to verify, and everybody needs to verify that the transaction is correct. And this transaction verification involves multiple steps. First of all, you have to check that some signature is correct so that the transaction was properly authorized. Maybe you can still design a system that allows you to do this, but you also need to check that the sender balance is greater or equal to than the outgoing amount, so that the sender had enough money to actually create this transaction. So how do we do that? Well, we use the proof paradigm to, in order to design a certificate, and the certificate should say that the transaction is valid. And then the miners in the system can simply check the certificate, be convinced that the transaction is valid, but without having to, ideally the certificate doesn't reveal any information about the details of the transaction. So how can we design this? Well, in general, this is called a confidential transaction, and we're going to use something called a cryptographic commitment. A cryptographic commitment is really the digital analog of an envelope. So you can write a value on a piece of paper and put it inside the commitment. This is called committing to a value. And the commitment has two properties. A, that it's hiding. Once the value is inside the envelope, you cannot see what the value is. But it's also binding. If I commit it to a value, like 5, then I cannot suddenly open it to a different value, 6. So this is the binding property. So we're going to use these cryptographic commitments in order to commit to all of the amounts in the transaction. And the goal here is just to hide the amounts that are being transferred. So still, though, we have this question of transaction validity. So in particular, we need to check that the sender balance is greater or equal to the outgoing amount. Sender balance minus amount is greater or equal to 0. And it turns out there needs to be a second check. We also need to check that the outgoing amount itself is greater or equal to 0. Otherwise, there's an attack. Yeah, I don't want to go into the details of how this works, but you can convince yourself that you actually need to do these 2 checks at once. So both of these checks have a similar structure. And what we really need to do is now design a certificate that says that some value, which is inside a commitment, is greater or equal to 0. So how do we design these certificates? So these certificates are called zero-knowledge range proofs. And we have some prover, so this would be the person creating the transaction, that one claims that here's a commitment and it is a commitment to a non-negative number. The prover then creates a proof pi using the commitment and the value inside the commitment and sends it over to the verifier. The verifier would be run by all of the miners in the system and everybody who needs to check the validity of the transaction. So the verifier is able to check the proof using the commitment C without knowing what V is, or actually having any information about what V is. And after checking this certificate, the prover is convinced that the transaction is valid, but it has no idea what the value of the transaction is. And it is convinced that it has no idea what the value V is. So it is convinced that it is positive, but it has no idea what the value V is. And yeah, so this is a zero-knowledge range proof. And in practice, we're not actually going to prove that a number is positive, but we're going to prove that it is in a small positive range. So between, say, 0 and 2 to the 64. And of course, this implies that the value is positive. But for that reason, we call it a range proof. So a zero-knowledge range proof is an instance of a much larger family of protocols called zero-knowledge succinct non-interactive arguments of knowledge, or for short, ZK snarks. And these go way back to the 80s, but there's been a lot of development on these ZK snarks in recent years. So in a ZK snark, I usually start with a circuit, and the circuit expresses some computation or some relation. And it's an arithmetic circuit, so a circuit that has addition and multiplication. And there's some private inputs to the circuit and some public inputs. We call the public inputs instance, and the private input is usually referred to as the witness. And the prover has access to both the instance and the witness. And the verifier, importantly, only has access to the instance and does not get to see the witness. And the first step is that we run a so-called setup algorithm, which takes as input the circuit and outputs a proving key and a verification key. The prover then uses the proving key, the instance X and the witness W, in order to produce a proof pi. It then sends it over to the verifier, and the verifier checks using the verification key, the instance and the proof, that this is in fact valid. So in our range proof example, how does this relate to our range proof? Well, in our range proof, the instance would be the commitment itself, and the witness would be the value V inside the commitment. And the relation would check that indeed C is a valid commitment to V, and V is in some small range. So for these ZK snarks, we need multiple security properties. So the 2 key security properties are knowledge soundness, in that which says that it's infeasible to produce a valid proof pi if the prover doesn't know a valid witness W. And the second security property, it's counterintuitive maybe in the beginning that you can achieve those at the same time, but it is this beautiful zero knowledge property, which says that the proof itself doesn't have to reveal any information whatsoever about W other than the fact that it exists. So the ZK snarks also have some important efficiency properties that we would want to achieve. So one of them is the so-called succinctness property, which says that the proof can be much smaller than the circuit. In fact, it can be logarithmic in the size of the circuit. I have a circuit of 1 billion gates, and the proof is on the order of 30 elements. And additionally, there's a verifiable computing property, which says that the verify algorithm can be much faster for running than evaluating the circuit itself. And this verifiable computing property allows us to outsource computation using these ZK snarks. So our goal is to build a very efficient ZK snark for these range proofs. And we have some particular efficiency and security goals for these range proofs. And if we remember back, what is the purpose of these range proofs? Well, the purpose is to authenticate these confidential, these private transactions. And because these transactions, they get sent around to every node in the system, well, we want to minimize the congestion in the system. So for that, we need these proofs to be very short and fast to verify. And ideally, they say less than a kilobyte, and verification time takes a millisecond. And also, we don't want the overhead for the prover, so the transaction creator, to be too large. Additionally, we have some security properties that we want to achieve. So ideally, these systems have minimal trust assumptions. And in particular, we have very efficient systems, but they use something called a trusted setup. So the setup algorithm is run by a trusted party, which then needs to properly discard the randomness that is used. It's sometimes referred to as toxic waste. Ideally, we build, because if this trusted setup is broken, well, then in this confidential transaction example, this can actually lead to counterfeiting. So someone who can break the trusted setup can print money out of thin air and counterfeit the currency. This is not just a theoretical consideration, but a system called Zcash, a blockchain called Zcash, they actually use such a trusted setup, and they then later had to disclose a vulnerability that could have led to an infinite counterfeit of their blockchain, of their cryptocurrency. So ideally, we build a system with minimal trust assumptions or no trusted setup, and minimal also other cryptographic assumptions. So we always want to build our cryptographic systems on kind of the most minimal assumptions that we can find. And unfortunately, the prior work you had to pick your poison. So either the prior work was incredibly large, so they had very large proofs, or they used a trusted setup. They were very efficient, but used this trusted setup. So our goal was to build a proof system that achieves the best of both worlds. And we did that in a work called Bulletproofs, which has short proofs and minimal trust assumptions. And the way that Bulletproofs works at a very high level is that you start with some circuit. So it's a ZK snark for a circuit. And then you compile it to something called the inner product argument. And we'll see in a second what this inner product argument looks like. And then there's a so-called Fiat-Shamir transform that allows you to make this into a non-interactive zero-knowledge snark. Bulletproofs is actually kind of two systems. So one goes from circuits to a ZK snark, and the other one is that we designed a specific protocol that is very efficient for these range proofs because of their tremendous importance in this application area. But both of them use at the core this inner product argument. So Bulletproofs is very efficient in practice, and it has very small proofs. So the size of these range proofs is a single range proof is 670 bytes. But also, if I want to scale the system for, say, larger computations, larger circuits, well, then it scales logarithmically, and it scales logarithmically with very good constant factors. So if I have a circuit which, say, has 1 billion gates, then the size of the proof will be, I think, less than 2.5 kilobytes. Additionally, Bulletproofs are very fast to verify, and we specifically designed a protocol that allows you to verify these proofs efficiently when you have many of them. So there's a batch verification protocol that allows you to verify many proofs at once more efficiently than you could verify a single proof. And for a range proof, this is on the order of half a millisecond. So what is this inner product argument, and what's the core idea of this inner product argument, and how does it work? Well, the idea of this inner product argument is that the prover has access to two vectors, A and B, so these are long vectors, and a scalar C. And it claims that C is an inner product of A and B. And the verifier has access to a commitment to these vectors, so a commitment to A, B, and C. And the commitment is compressing in that the size of the vectors may be size n, but the size of the commitment is constant size. And then in every step, the prover creates two so-called cross terms, we'll see in a second what they are, and sends them over to the verifier. So these are two, it creates these cross terms and then commitments to these cross terms and sends them over. So it sends over two terms, two commitments in every round. And then after this round, we end up with new values for both the prover and the verifier. So the prover can compute these values A prime and B prime. So these are now also vectors, and a new scalar C prime. And we still have an inner product relation between these new vectors. But what has changed is that now these vectors are of half the size. So we went from vectors of size n to vectors of size n/2. And the commitment, the verifier at the same time can compute a commitment to these same values. And if now this new claim holds, well, then we can show that if this new claim holds, then the old claim would have held, if and only if. So of course, we're not just going to do this once, but if we're able to reduce the size by half, well, then we're going to run this multiple times. And in particular, if we run this a logarithmic number of times, then we end up with constant size vectors. So the prover ends up with constant size vectors, and the verifier has a commitment to these constant size vectors. And the prover can then simply open the commitment, send over these constant values, and the verifier can check that this simple multiplicative relation holds between these values. So overall, the total communication that the protocol requires is actually just these two values in every round. So it has total communication of 2 log n commitments. And it turns out that the verifier has to do O of n work in order to basically open the final commitment. So what is this reduction step? How do we get from n/2 to n, from n to n/2? Well, really, what we can look at is this is really a linear trying to reduce 2 inner products to 1 inner product. And so say we have 1 inner product here, so A, B, and the inner product of A and B, and another inner product, A prime, B prime, and C prime. And I somehow want to reduce these 2 inner products to 1 inner product. So what I'm going to do is I'm going to take a random linear combination using a variable x. So A plus x times A prime and B plus x inverse times B prime. So now this gives me 2 new vectors, also of size n/2, but really these are polynomials in n. And if I look at the inner product of now these linear functions in x, I get that the constant term is actually just the sum of the old inner products, so C plus C prime. And then it turns out there are some more so-called cross terms. So I have x inverse times the inner product of A and B prime, and x times the inner product of A prime and B. So how does this this identity, how does this give us a protocol? Well, the prover is simply going to send these cross terms, so the inner product between A and B prime and A prime and B, compute them and send them over to the verifier. And then the verifier or the prover and verifier will together sample a random x and check that this identity holds at this random value x. And it turns out that if it holds at a random value x, then it will hold with high probability for all values x. And we can use this to show that if this final inner product is valid, well, then this can only be true if the original inner products were valid. So this is the inner product argument reduction. And let's now take a look at how this manifests in terms of the full system. And in particular, we're going to look at the proof size of bulletproofs. And we're going to compare it with both the old range proof that was used and that didn't have a trusted setup. So for example, this was used in a system called Monero before they deployed bulletproofs. And also then there are these ZK snarks, which are, as I mentioned, are incredibly efficient, but unfortunately they use the trusted setup. So for range proof, the comparison is that bulletproofs, the one range proof is less than 700 bytes versus roughly 4 kilobytes for the old range proof system. But interestingly, bulletproofs also have this logarithmic scaling. So usually in these confidential transactions, I need to do at least 2 proofs. And here the old system scaled linearly versus bulletproofs, which scales logarithmically, so it's almost the same size versus now 8 kilobytes for the old system. And it turns out that in Monero, you actually have much more range proofs. They basically add some decoy transactions for additional privacy. And there, the comparison is from 40 kilobytes to less than a kilobyte. Additionally, bulletproofs are fairly fast to verify. And in particular, they have this fast batch verification protocol. This is this gray line here. And we compared this to ECDSA signature verification. And the reason why we compared it to ECDSA is because standard non-confidential transactions also have to do signature verification, versus confidential transactions now would have to do this batch verification of bulletproofs. And it turns out that at least for larger transaction sizes, these are almost the same.
A short question about your technical slides from before, which is where the X and the X inverse are from which domain?
So this is all done over a field, and usually, so they're from some exponential, we do this over an exponentially sized field, and you usually, so the protocol is that the verifier samples a random X in this domain, and then we use that, but it turns out in the full pipeline, you can actually remove the interaction and make this non-interactive.
Thanks.
Okay. So numbers being small, and these trade-offs seem to are beneficial, but what does this mean in practice? Well, Monero, which is the largest private blockchain, actually decided to deploy bulletproofs. So they switched from these old range proofs to bulletproofs, and it led to a reduction in transaction fees by 97%. And the reason is that the network before was very congested. And then because these bulletproofs are so much smaller, it basically removed the congestion and drastically dropped the transaction fees. So bulletproofs has had significant impact. There's a lot of other very nice schemes that are using ideas from bulletproofs, or they're building on top of bulletproofs. And yeah, there's a lot of really nice work that is happening there. There's multiple high performance implementations and that are open source from different people. There's a lot of amazing work being done on further analyzing the security of these systems, giving tighter security bounds, analyzing in the non-interactive settings. And as I already mentioned, it's being deployed in many practical systems today. So Monero, I think the largest private blockchain, has over 30,000 transactions alone, but it's also deployed in even systems by Chase. They have a private blockchain which also uses bulletproofs. So now moving on to the second part of the talk, I want to talk about leader election and green leader election using something called verifiable delay functions. So before we talk about green leader election, green and fast consensus, we first have to understand why blockchains, and in particular Bitcoin, is so incredibly wasteful. And it really comes down to the use of this proof of work algorithm. So basically, in order to participate in the Bitcoin system, I have to do an expensive computation, and my stake, my share in the system, my voting share in the system, is proportional to the amount of computation that I do. So it's a proof that I've done some work. And basically, this turns into a competition of who can do more computation, and this then leads to more energy usage and more energy wasted. Fortunately, though, so this is Bitcoin and Ethereum today, but fortunately, most modern systems are using different protocols, mainly because of this wasteful nature. So for example, they use something called proof of stake, where your voting share is proportional to the amount of tokens that you hold, or in the amount of money that you've committed to the system. And additionally, there's something called proof of space, where your voting share is proportional to the amount of space that you've allocated to a hard drive. And so, for example, Ethereum is going to switch from proof of work. I think this year they're going to switch to a proof of stake system. And both proof of stake and proof of space are using as a key tool, or at least the most efficient systems use as a key tool, something called VDFs and verifiable delay functions, which I'll talk about today. So to understand where these VDFs come in, we need to understand that Bitcoin consensus really runs at its core, or blockchain consensus runs at its core, a lottery. And this lottery is run in order to elect the next leader who gets to add the next block to the blockchain. And for Bitcoin, this is the so-called proof of work lottery. So it's a computational puzzle, and the first person to solve the puzzle gets to add the next block to the blockchain. So we start at some state, and then we have this proof of work lottery, and some person solves the puzzle first, so wins the lottery, and gets to add the next block to the blockchain, and so on and so forth. So the problem is that this proof of work consensus is incredibly wasteful. And what this computational puzzle is essentially these miners trying to find some values, some small hash values. And every single participation, it's an embarrassingly parallel computation. So the more computational resources I have, the higher my probability is of winning this lottery and solving this puzzle first. And this basically ends up in these miners running really expensive server farms, trying to get as cheap as possible electricity, and yeah, really doing a lot of computation. Unfortunately, you might think, oh, well, I mean, maybe they're doing useful computation, but it turns out that this proof of work puzzle is inherently not useful. We don't know, like, it spits out small hash values, but we don't really have any use case for these small hash values. So it's a not inherently useful computation. But fortunately, this view of the system gives us a very easy attack point of how can we design a lottery that doesn't use this wasteful proof of work system. And once we've done that, well, then basically we've solved the environmental problem of blockchains. And this is very related to an old primitive called a randomness beacon, which is what we would need is an ideal service that somehow regularly publishes random number, which no party can predict or manipulate. And if I have such a random value and a random number, well, then it's very easy to design a lottery from it. I simply take the random value, modulo the number of participants, and this gives me the index of the leader or something along those lines. So these randomness beacons, they have applications to lotteries, but they also have other applications. So that, for example, they can be used in smart contracts or in other cryptographic protocols, such as voting protocols. And it's very easy to design such a random beacon if I have a trusted party available. And this actually exists. So NIST regularly publishes, I think every minute or so, publishes a random value, which no one but them can predict or manipulate. We actually do this even more often in real life. We run a lot of lotteries in many systems. So for example, there's the green card lottery, or for sports events, there's lotteries in order to, and well, there's financial lotteries. And the problem is, and we do this by drawing balls out of a bin and making a big show. But the problem is, can we really trust these trusted parties? Well, I think there's a really funny example here that illustrates how this can go wrong. So the UEFA, which is the European Soccer Association, draws the games of the Champions League. So who gets to play whom? And it actually turns out that, so they do this in a TV show, and then Sepp Blatter, who's the former head of FIFA, so the World Soccer Organization, now very disgraced, but he actually said in an interview that UEFA was cheating. And the way that they were cheating is that they froze the balls. So they were drawing balls out of a bin, and they froze the balls of the teams that they wanted to play against each other, because it would increase the TV revenue or for whatever reason, right? And then the person drawing would shuffle around and grab the ball that is frozen, because they could feel it, and put it in and get the draw through that. And it's obviously, you on TV, it looks perfectly fine. You can't tell that this is happening. And we also now don't know if this is a true story or not, but you can't really verify, really. We don't have a verifiable lottery where we can verify that everything was correct. So how can we build a random beacon? So let's assume all of us here in the room want to build a random beacon, an ideal service that regularly publishes these random values. Well, one thing that we could do is that we all simply say a random number. We flip some coins locally and then say a random number and say it publicly out loud or post it on some bulletin board. And then we take the output of this, hash it, and this gives us the random seed. Well, the problem with this works if we're all honest, but the problem with this is that Zoe really controls the final seed here. So Zoe, the last person to submit, can choose her random value based on everything she's seen before and heard before, and really manipulate the seeds in that way. Because she can just simply, she will try different RZ values in order to see which one it works. So the solution for this is to slow things down. So ideally, we use something called a slow function, which is a function that takes a long time to compute. It's non-parallelizable. And we say we know it takes like a minute for everybody to say their value. Well, then we'll use a slow function that takes an hour to compute, even on a parallel hardware. And we then take the output of this slow function as our random beacon value. And now the idea is that Zoe doesn't have the time to test which values of our Z are going to affect the beacon output. So we need to, yeah, so basically she can try different values, but she doesn't know which one are going to help her. And it turns out that as long as just one party is honest, the system actually gives you a beacon value. So the problem with this solution is that we used a slow function. So what this means is if I want to check that the beacon is correct, well, then I need to rerun the slow function. So the verification of the system is very slow. And this is problematic in multiple applications, but in particular, it's also problematic in the blockchain consensus application. Because here we run this lottery every single iteration. And now if I want to catch up, I need to constantly verify these new beacon values and constantly redo the computation. So it might be, for example, very impossible for me to catch up with the computation. So the verification can't actually be slow. There's also other reasons more deeply related to the consensus protocol why I want this verification to be fast. So with this in mind, we defined and we came up with this notion of VDFs, or verifiable delay functions. And what are they? Well, it's really all in the name. It is a function, which means that there's a unique output for every single input. It incurs a delay, which means that it can be evaluated in time t, but can't be evaluated in much faster than t, even on a highly parallel machine. And it is verifiable, which means that it is slow to compute, but fast to verify. So for example, inverting the function is fast, or we're going to use the prover paradigm to such that the evaluator produces an additional proof that the beacon was computed correctly. So now how can we use this VDF? Well, we're going to use our VDF as a slow function. And as we use the function property to say that the output is unique, right? It's a unique output. And the slow function now gives us the seed, and this gives us the beacon value. And now in order to verify it, I simply use the verifiable property of the VDF in order to check that the consensus, that the beacon has the right value. So when we use this for our blockchain consensus, let's step back a little bit and try to think about the overall goal was to reduce the environmental impact. So we're still doing some computation here. And how does this relate to the environmental impact? Well, the important thing is that instead of proof of work, we're now running these VDFs. And for these VDFs, only one honest party has to run this VDF, and then it can prove to everybody else that it ran the VDF correctly. So everybody else just needs to check the computation. So really, there's no, there's almost limited, there's very limited wasted computation here in order to run our protocol, in order to run this consensus. So we came in our initial work, we defined VDFs and gave some security properties and gave some applications, and also came up with an initial proposal for verifiable delay functions. But it's been really amazing to see there's been a tremendous amount of follow-up work very quickly after people came up with other very beautiful VDF constructions for example, based on exponentiation modular composite. And then the latest kind of VDFs, and the one that is, I think, going to be deployed in Ethereum, is based on something called accumulation-based incrementally verifiable computation, which is also something that I've done a lot of work on. VDFs have, as I mentioned, they've had a lot of academic impact. There's a lot of very nice follow-up work. People have shown that this can enable some new cryptographic tools. And there's also really interesting complexity theoretic implications that people have shown for VDFs. It's also had significant industry impact in that it's being deployed in multiple systems such as Chia and Filecoin. And there's also this multi-million-dollar VDF alliance, which is an industry alliance whose goal it is to fund research around VDFs, but also build specific hardware for evaluating these VDFs. So I want to conclude by saying that these blockchains still have some problems today, but that actually these problems are solvable and that we can build tools that address these problems head on and really remove these limitations of blockchains. I also want to talk a little bit about the future outlook of where I see the space going and where I see my personal research going. So one area that I'm very excited about are smart contracts. So we've seen, for example, how we can get privacy for simple transactions, simple transfers of values, but blockchains also have these smart contracts, which enable complex interactions between multiple parties. And there's a lot of research questions around them. How can we design privacy for them? How can we keep maybe the smart contract itself private? And also there's scalability questions. Can we maybe build ZK snarks in order to outsource the computation of these smart contracts? Another area that I'm really interested in is around CBDCs, or centrally banked digital currencies. So a lot of central banks have already mentioned that they're going to build digital currencies. And we don't really know what they look like yet, but there's kind of different proposals for them. So China, for example, has said that they're building, or they've described the design of a centrally banked digital currency that gives the government a lot of control and has very low privacy features for the users and is really a means of currency control. The Federal Reserve in Boston, for example, put out a paper together with researchers at MIT, which was a proposal for a centrally banked digital currency that had much better trade-offs between privacy and transparency in governments. And I think these next coming years are going to be very important for us as technologists to engage with policymakers and to really show them, provide the right solutions for them, and such that these centrally banked digital currencies are a tool for innovation and a tool for good and not a tool for suppression and currency control. I also think that my research, so we've seen with these blockchains a tremendous amount of application of these proof systems and the real first wide-scale deployment of these proof systems. But I think they will have much more applications beyond blockchains. So, for example, they can be used for cloud computing, for private auditing, and we've already seen lotteries, which of course have many applications beyond blockchains. In conclusion, I want to say that blockchains hold an amazing promise. They can really improve and revolutionize the financial system, which can have tremendous follow-on effects, but they still have many challenges today. But my research uses a common proof paradigm in order to try to overcome these challenges. And finally, I want to say that reiterate that this is really a beautiful open research areas that includes all of the areas that are listed here, but also many beyond that, programming languages for formally verifying smart contracts, and of course, system security. And I think there's a lot of beautiful work here that can be done, especially at the intersection of all of these areas. So thank you very much.
All right, so thank you, Benedikt, for a very nice talk. There is already one question that I postponed to now, and then everyone else who has questions, feel free to raise your hands, and then I'll move to that. So Anoop was asking, I don't know if you want to ask it yourself, but I think if I phrase it correctly, whether you can explain the connection with existing literature on leader election is a very old problem. So what's the difference between what's going on here and the existing old protocols?
So the key difference is that these old leader election protocols, they basically, I think the best ones that we have, I think you need 2/3 of the parties to be honest in order to get a leader election protocol. And even more so, they usually require a lot of interaction between different parties. And this VDF-based beacon only really requires one party to be honest. It uses different kind of assumptions. It really is based on these timing assumptions, but it's okay if, as long as one party is honest, the beacon will be unbiasable. And additionally, it's a single shot protocol where that is very efficient and very streamlined, where everybody just has to say a random value and then you just compute the VDF, and that has a lot of benefits as well.
Let me just ask one question again on that. So you presented this as relying on a bulletin board, But if I think of this as a full bulletin board, I kind of need almost a blockchain to do that, right? But you're sort of bootstrapping something that allows you to do the blockchain. So how can you get around that? So maybe can you?
Yeah, I mean, I guess so. What really happens is that usually, actually, in these systems, you do use the blockchain as the bulletin board. And what essentially happens is that you don't usually just have one leader, but you elect a small committee of leaders. And then they basically initialize the VDF for electing the next committee of leaders. And you really want them to be unbiased. So just by basically them, they have to speak up anyway. So this gets basically communicated anyway, and then you can use you can use that to initialize the next leader election.
Okay, there's another question. Thank you. There's another question in the chat. So does the time cost of the VDF have an effect on the overall transaction rate the system can achieve?
It's really about the delay properties in the network. So what time properties in the for the VDF do you need to have? Well, you need to be able to show that the VDF is long enough that it basically covers the time where any honest party would have submitted their value. And that depends on the network delay, which is then, informs you of how long you need to run your VDF. So it does have some connection there, but it almost even goes, and of course the network delay is related to the number of transactions. So there's some indirect relation there in that, you basically have one block per, or one leader election per VDF. And the longer the slower your network is, the slower you need to make your VDF. And which then slows down the number of transactions, I guess, yeah. So it's kind of, it almost goes both ways, I would say. It's in the end, really what matters is the network speed.
So in this version of the system where you're changing the role, so where does the designation of who becomes a miner coming in the systems that you've described? I mean, obviously in something like Bitcoin, you're actually creating Bitcoins at some point by, additional Bitcoins get created in that process, and doesn't seem necessarily to be part of what you're doing.
Right. This is why, like what I've described is really a leader election amongst kind of an already existing set of maybe users or public keys. But there's this very good question of like, who gets to even participate in the system? And this is where this proof of stake and proof of space part comes in. So basically in proof of stake, the amount of shares that you have is proportional to the amount of token or stake that you have in the system. Versus in proof of space, this is, this is like there's a whole classes of protocols here, but basically in proof of space, it is proportional to the amount of hard drive space that you are able to allocate.
David?
Yeah, actually, just to kind of follow up on that a little bit, that one of the problems that I think we saw with Chia and stuff was that it's hard to call them green blockchains because they rely on that proof of space, which means if there's a reward structure that rewards having space, what you do is you buy a lot of space, which means we have a whole bunch of drives that are doing nothing. So sure, we're not spending electricity on computation, but we're spending resources on producing useless drives. And then similar with proof of stake, we instead see that the goal is simply to centralize, because whoever puts in the most stake gets the most rewards. And so it kind of stops being centralized that way. I think I'm more interested in kind of the proof of space and like, is there a greener version of that? Because Chia kind of didn't land.
So I think with Chia, what we saw so Chia is one of these proof of space systems. And certainly what we saw in the beginning is exactly what David was saying, that people are starting to buy and buy up hard drive space, and it drove up the price of hard drives tremendously. What actually happened, which is kind of interesting to see, is that the hard drive space exploded exponentially, and then it's like fairly flat now. So once these hard drives were filled and bought, and there was kind of, I guess, in the beginning, some arbitrage to be made by buying hard drives and filling them, like now it really seems like that you know, this is leveling off, and it doesn't lead to as much you know, hard drive allocation anymore. And it's also importantly, I guess it's a one-time consumption of resource versus proof of work is a continuous consumption of resource. I do though overall agree with the point that, you know, filling hard drive space is like, maybe it's greener. Is it really that much better? I don't know. There's one alternative, Filecoin, which basically runs a similar protocol, but where the idea is to use the hard drive space for something useful. So for backing up, for building a file storage system and backing that up, and they have a very complicated but very nice protocol for enabling that. I don't know like what the end all be all is there. For proof of stake, I mean, the centralization aspect is, I'm not sure whether that's true that it's so much centralized. It certainly is. I mean, one argument that people say against proof of stake is that the rich get richer, the people who already have stake in the system get to participate more. But to be honest, there's a counteracting force, which is that usually the reward is newly printed tokens. So who, like, this is inflation. So who basically loses out from inflation? Well, already the people who have stake in the system. So it really like is more of a balancing force that you need to participate in the proof of stake in order to not lose out on inflation. It's like, you know, not participating is basically then you get paid the inflation fee. I mean, I think all of these systems have pros and cons and different trade-offs. And, you know, proof of work has some very nice properties. But I personally think that proof of work is simply, because of its ecological impact, completely unacceptable. So we need to look for alternatives. And that they're perfect. Are they perfect? No, probably not. But I mean, this is, you know, opens up research opportunities.
Thanks.
So I think we can then virtually thank Benedikt again and end the talk here.
Thank you very much. Thanks for having me.